When you look up at the night sky, it's pretty easy to assume we basically have it all figured out, right? We know about the Big Bang, we know about galaxies, and we know the universe is expanding. But look, right now, behind the closed doors of the world's leading observatories, there's actually a growing panic, a very real possibility that our fundamental understanding of reality might literally be falling apart. And I want to be clear here. This isn't science fiction. It's not some fringe internet theory. This is a genuine, full-blown crisis being discussed by the smartest astronomers on Earth, like John O'Meara over at the Keck Observatory, because the data pouring in from our newest, most advanced telescopes is directly contradicting the core physics we have relied on for nearly a century. So welcome to this explainer. Today, we're diving straight into the biggest mystery in modern physics, the Hubble tension. We're going to look at why the James Webb Space Telescope is finding things that absolutely shouldn't exist, and what all of this means for the very fabric of our universe. So let's start with the big question. Is the universe broken? When we launched the James Webb Space Telescope, the whole goal was to look further back in time than ever before, right to the dawn of the cosmos. Now, our standard models firmly dictate that early galaxies should be small, simple clouds of stars that just sort of gradually grew over billions of years. But Webb is finding something completely different. Just 500 to 700 million years after the Big Bang, we're seeing these candidate galaxies literally dubbed universe breakers. Why? Because they contain up to 100 times the expected stellar mass for that era. And by 800 million years, we see things like JWST's quintet. That's 5 massive galaxies already interacting and forming stars at blistering speeds. There are even these ultra-massive systems called red monsters that are forming stars with double the expected efficiency. There is simply no way they should be there. They're essentially speed-running star formation. Joel Leja, a researcher at Penn State, hit the nail on the head when he said this actually creates deep problems for science. Because if our timeline of the universe is wrong, it means the very engine driving cosmic evolution is completely misunderstood. And that brings us directly to the absolute core of the current crisis in astrophysics, which is what scientists call the Hubble tension. This is the granddaddy of all cosmological mysteries, and it revolves around one specific, incredibly stubborn number, the Hubble constant. Ever since Edwin Hubble first calculated it way back in 1929, penning down this exact rate of expansion has been the holy grail of astrophysics. Because the Hubble constant doesn't just tell us how fast galaxies are flying away from each other, it's the mathematical foundation that dictates the history, the size, and the ultimate fate of reality itself. So why does this matter to us? Well, because of this number right here, 13.8 billion years. That is the accepted age of our universe. But if our measurement of the Hubble constant changes, this number has to change with it. If the universe is expanding faster than we thought, it means it reached its current size much more quickly, which would make it significantly younger than 13.8 billion years. So yeah, the stakes are astronomically high. To figure out why this is happening, we have to look at the 2 different ways we actually measure space. It's kind of like a cosmic tug of war. Depending on how you measure the universe, you get 2 completely different answers. On one side, you have the early universe probe team. They look at the cosmic microwave background. That's the leftover radiation from the Big Bang, mapped out by the Planck satellite. They take our standard model of physics and use it to predict what the expansion rate should be today. On the other side, you have the late universe probe team. They look at the local universe right now using standard candles, like exploding supernova, to directly measure the speed of expansion as it's happening. The crazy part? Both methods are incredibly meticulously precise, but they violently disagree. And here is the Hubble tension laid out plain as day. The early universe CMB method predicts a slower expansion rate of 67.4, but the local late universe measurement from the SHOS collaboration, they demand a much faster 73.04. And to make things even more complicated, an entirely independent late universe probe using time delay cosmography, which tracks how massive galaxies actually bend the light of distant quasars, well, that points to 71.6. These margins of error do not overlap. Someone or something is fundamentally wrong. And just when we thought the Webb telescope would clear this up, it actually deepens the mystery. For a while, we basically assumed older local measurements from the Hubble Space Telescope were just slightly flawed, maybe blurred by space dust or a tiny calibration error. So scientists like Wendy Friedman at the University of Chicago used the James Webb Space Telescope to cross-check multiple standard candles. Think of these standard candles as cosmic streetlights. Because we know exactly how bright a Cepheid variable star or a carbon star actually is, we can measure its distance by how faint it appears to us. Webb observed these stars with unprecedented clarity, completely stripping away the cosmic dust that clouded previous measurements. But rather than definitively solving the problem by matching the 67 or the 73, Wendy Friedman's new JWST analysis landed right smack in the middle, around 70.0. So Webb effectively confirmed that the tension isn't just some simple equipment error. The discrepancy is absolutely real. Our early universe predictions and our late universe realities simply do not match. Which leaves us with a terrifying but kind of thrilling conclusion. If the telescopes are working perfectly, and all the evidence says they are, then the standard model of cosmology is missing a massive piece of the puzzle. Now, finding something wrong in physics is actually a scientist's ultimate dream, because it forces us to find completely new ways to measure reality, unlocking a much deeper understanding of nature.
So, what if we stop looking at starlight altogether and start listening?
Enter the era of gravitational wave astronomy. We're talking about cosmic sirens. When massive objects like supermassive black holes smash together, they send physical ripples out through space-time itself. Recently, the Nanograph collaboration announced evidence of a persistent background hum of these low-frequency ripples, and they did it using a galaxy-sized array of dead stars called pulsars. By analyzing these gravitational waves, we completely bypass all the optical illusions and the dust that mess with standard telescopes. And the result from this calibration-free gravitational measurement, specifically from the recent LVK GWT C5 catalog, they got a Hubble constant of 71.0. This is absolutely fascinating. It's perfectly consistent with the higher late universe measurements, yet it's an entirely independent method. It's a massive leap forward, for sure, but admittedly, it's still not precise enough to officially declare a final winner and solve the tension once and for all. So, how do we fix this cosmic model? Well, if the tension is real, we need entirely new physics to explain what happened between the Big Bang and today. And theorists are throwing out some absolutely wild, groundbreaking ideas to make the math work. One of the leading theories is early dark energy, a mysterious force that might have caused a brief, violent burst of expansion right after the Big Bang, essentially shrinking the sound horizon before fading away entirely. Others suggest undiscovered particles, like sterile neutrinos, or maybe even new types of dark radiation that alter the universe's early growth spurt. But to actually prove any of this new physics, we need a bigger net. And for that, we are waiting for the Nancy Grace Roman Space Telescope, set to launch in late 2026. Sitting a million miles away at the L2 Lagrange point, Roman is going to open a field of view 100 times larger than Hubble's. It's specifically designed to map out dark matter and dark energy on a scale we have never seen before, tracking the expansion of the universe over vast stretches of time so we can see exactly where our current model breaks down. We are standing on the precipice of a massive paradigm shift. The Webb telescope's impossible galaxies, the relentless Hubble tension, and the humming of gravitational waves are all pointing toward a reality far more complex than we ever imagined. Thank you for joining this explainer. Keep your eyes on the stars and your minds open, because the textbooks, they're about to be rewritten.